got another test called the direct comparison test. And these tests are really cool because a lot of times the series that we deal with are not easy to determine whether or not they converge or diverge. So what we do instead is we compare them to series that we do know converge or diverge. So for instance, we've learned a couple of very special series and when they converge and diverge. We've learned about geometric series, right? Geometric series that look like this will converge in what situation? When do geometric series converge?
Whenever R is less than 1.
Whenever R is less than 1, but also greater than -1. Okay, when it's a fraction, but it's also it could be a negative fraction and it also converges. So we know that it converges in this interval for R. Well, we also learned another series just now. We learned about p-series. And p-series are very easy to determine if they converge or diverge. How do I know when p-series converge?
When it diverges?
How do we know when p-series, 1 over n to the p, converges?
When it's greater than 1.
When p is greater than 1, right? So we already have 2 very particular series that we know converge or diverge. So now we want to take a look at this series, okay? This right here is not a p-series because it doesn't look like 1 over n to the power of p. It doesn't look like n is the base. It looks like n is the exponent. So because I see n and an exponent, now I start to think, well, maybe this is like a geometric series, but it's also not a geometric series because it doesn't look like a single fraction to a power. I got this extra +1. So what we do, and this is a pretty basic one, but this is going to be the same general idea, is that we say, you know what, let's compare this to a series that I know about its convergence. So if I were to get rid of this extra little +1 on the bottom, wouldn't that just become 1 over 2 to the n now? And the reason I would get rid of that +1 is because that little +1 in the denominator is going to be so insignificant when I go all the way out to infinity that it's not even really going to matter eventually. So what I'm going to do is we're going to compare this particular series, okay, with some other series. Now we know that this series is the same as 1/2 to the power of n, and 1/2 to the power of n converges because it's geometric. Well, now we've just got to think about the fact that, about this little inequality here, okay? And this is the general idea about the direct comparison test. The direct comparison test is essentially saying, let's assume that I have some series, okay? And I'm trying to determine whether or not this series right here converges or diverges, okay? Now, I don't know whether or not this series converges or diverges. And let's call that series A sub n. But let's say that I compare it to another series. Or maybe I compare it to this series right here. Let's call that B sub n. All right, well, if I could prove that from 1 to infinity, okay, this series right here converges, then doesn't that mean that essentially all of those terms would have to add up to a certain number? Or if I were to think about it in terms of the integral, if B sub n converges, wouldn't that mean that the entire area under the curve goes to a fixed number? Well, if I know that my original sequence A sub n is underneath the convergent sequence, and I already know that this sequence right here converges, then wouldn't this value right here, if A sub n is less than B sub n, and B sub n converges, wouldn't that automatically force A sub n to converge? Meaning if the area underneath B sub n goes to a fixed number, and A sub n is underneath that value, then I know that that's automatically going to have to converge to some number as well. So that's one situation with the direct comparison test. And so the comparison test is to pick some sequence that we're going to call A sub n. Not pick a sequence, that is the original sequence. Okay? But we're going to pick a sequence to compare that sequence to that looks kind of like it. And that shows us that 1 over 2 to the n plus 1 is definitely less than 1 over 2 to the n. Can anybody tell me why I know that? How do I know that 1 over 2 to the n plus 1 is smaller than 1 over 2 to the n?
Because the denominator of b sub n is always going to be 1 less.
That's right. So if the denominator is greater, then the fraction is smaller. So I know that this fraction is smaller than 1 over 2 to the n. And therefore, by the direct comparison test, we just simply demonstrated that this series converges, and therefore this series is going to converge to something less than 1, because I know that this series converged to 1. Now, the direct comparison test could also be used in another circumstance. It could also be used in a circumstance where I compare this to a sequence like this, that's maybe completely underneath the purple one. Let's now call this B sub n. And now let's assume that B sub n diverges. If you think about what that means, doesn't that mean that the area here is going to go to infinity? Well, if the area under the divergent sequence or series is divergent, then wouldn't that mean by adding more area, I'm just adding more area to something that's already infinite? So the direct comparison test can be used in two very particular circumstances. Okay, one circumstance when A sub n is less than B sub n and B sub n converges, or in another circumstance where A sub n is greater than B sub n and B sub n diverges. The easiest way to remember when it can happen is by remembering this graph. Is by recognizing that if a series is smaller than a convergent series, then A sub n must converge. Or if A sub n is above a divergent series, A sub n must also diverge. Any confusion on that idea?
Not on that, but could you explain how we went from like the an less than bn? How come we rewrote it as like 1 over 2 to the power of n?
Yeah, because we were comparing it. Notice that A sub n was the original series that I started with. A sub n was right here. So A sub n is always representing your original sequence. Okay. Now, I don't know whether that sequence converges or diverges, but I do know that this geometric sequence converges, right? So I know that that's the series of that. That's geometric. It's 1 over 2 to the power of n. I know that that converges. And 1 over 2 to the n is pretty damn close to 1 over 2 to the n plus 1. Really, really, really close. So if I could look at something that's similar to the given series, and I can prove that the original series is smaller than this convergent series, then I can guarantee that this situation right here occurs, which is underneath a convergent sequence, which forces A sub n to also converge. So the purpose of this is that you're trying to pick some other sequence called B sub n that will help you to determine whether or not the original series converged.
But how
really
come
more
we
or less-
wrote it as 1/2
Go ahead.
to the n power?
Say that again?
Like my question was like, how come we rewrote it as 1/2 to the n power?
Oh, because this right here doesn't look to me to be geometric. This does,
Oh, okay.
right? So I'm trying to rewrite it as a geometric sequence. That's why. So why you're saying, why did I write 1/2 to the n as 1/2 to the power of n? And it's just so that I could write it in the form of a geometric series.
Thank you.
Okay? Yeah, thanks for clarifying that. All right. So let's take a look at the direct comparison test here. So the direct comparison test is just saying, let's suppose that we've got two different series, okay, with positive terms. And let's assume that we're trying to determine whether or not A sub n is convergent or divergent. So what we do is we pick some particular value or pick some particular series that we know about its convergence or divergence. So we take the sum of B sub n is convergent. And we recognize that the original series or sequence is below the chosen sequence. Then that must imply that the original series converges. But if the original series that we choose diverges, and I see that my original series or sequence is above my chosen sequence, then that tells me that the series is divergent. This is a lot to remember right here, which is why I would suggest understanding this graph. This is what really the whole point of this problem is. Understand the graph so that you could say if the sequence is underneath a convergent sequence, then the series converges. If the sequence is above a divergent sequence, then the series diverges. And that's what I would suggest you recognize and remember. Okay. A lot of times the tough part is determining an appropriate choice for B sub n. And sometimes you choose something for B sub n and it's still inconclusive. You can't quite tell. So you choose something different for B sub n. Okay. So what we want to do here is we want to maybe compare ln of n over n to something that we know converges or diverges. Well, remember, I normally want to pick P series or geometric series. And so I'd say that this most resembles 1 over n, but I can't quite say that it really resembles 1 over n because if you look here, ln of n is not the same as 1, right? But I could see that eventually, if 1 is just a horizontal line and ln is a curve that increases, eventually, won't the natural log function get larger than 1? So eventually the natural log function will get larger than 1. In fact, if we want to be a little more specific here, then we could actually see when that actually happens. So let's go ahead and compare them when n is equal to 1. When I plug in 1, I get that 0 is less than 1, so that didn't happen. If I keep plugging in numbers, I could continue to see if it works, but I'm going to plug in e just because e has an easy natural log. So I could see that the natural log of e over e is the same as 1 over e by the time I get to e. So even though there isn't technically an e term because e isn't an integer, I'm thinking of this maybe in terms of a function. And I could see, sure enough, it looks like there's some point to where the terms start to cross, which hopefully makes sense because if you take a look at the graph, okay, I could see that 1 looks like this, while the natural log looks like this. So eventually, eventually, isn't there going to be some place where this function exceeds this function? And so when that's going to happen is when n is greater than or equal to 3. So we know that 1 over n is divergent because it's a p-series where p is equal to 1. So 1 over n is divergent. But wait a second, we know that the natural log of n over n is above a divergent sequence. So if this one already goes to infinity, and this one is larger, then this will even go to a larger infinity, which means that that series diverges by the direct comparison test. And that's what we state, okay? Pretty cool in that?
So that's the second like case if an is bigger.
Yeah, so that's basically, so the first one showed that, that's the first one showed if you choose a sequence that where the original sequence is smaller than a convergent sequence, then the original series converges. But we could also determine that if the original series is larger than a divergent series, then I know that the original series also diverges. Cool.
Why do you pick 1 over n for b?
Because it's the best choice that's close to that series. Because if you look up here, okay, let's say that I wanted to compare, for instance, 1 over 2 to the n plus 1, and I want to compare that to 1 over n squared. Which of these is bigger?
And
It's really hard to tell which one is bigger because they don't really look anything like each other, okay? So that's why instead I say, you know what, let's not choose n squared. Let's choose 2 to the power of n because I see a 2 to the power of n right there. So it seems reasonable to just cancel out that little constant and rewrite it as 1 over 2 to the n. So I'm choosing something that's going to actually be similar to the original series. Now this one right here, I could see it's got a natural log on top, but I don't know any series that are convergent or divergent by just looking at a natural log. I only know about convergence and divergence of p series, 1 over n to a power, and geometric series, r to a power. So the best choice here is to just say, well, I see that this has a denominator of n. P series have denominators of n. So I'm going to choose a p series to compare this to, and I'm going to compare it to 1 over n. That's really the only thing that we could say. It's basically saying, what does this most resemble? And so we're going to choose 1 over n. Okay. Now, there's certain times, though, that the direct comparison test won't work. And that's like if you come up with a situation like this, okay? Let's say that you see 1 over 2 to the n minus 1. And you decide, I'm going to compare that to 1 over 2 to the n. Which one of these is bigger?
Bn.
Yeah, this one over here is actually larger because notice that it's got a larger denominator, or this one is smaller because it's got a larger denominator. This denominator is larger than this one, right? If you've got a larger denominator, the fraction is smaller. So that must mean that a sub n is bigger than b sub n. But what do we know about b sub n? Does that converge or diverge? It's a geometric series where r is 1/2, so it obviously converges. R is 1/2. Okay, but that doesn't help me because if you take a look at if you think about the graph, if I just give you a graph right here, okay, and I were to draw A sub n, okay, if this is A sub n right here, and I know that A sub n is larger than B sub n, if you know that B sub n converges from 1 to infinity, okay, if B sub n converges, and then A sub n needs to add more on, the problem is I don't know if the extra that was added on for that series is going to cause it to converge or diverge. So this is why the direct comparison test can't be used, because the compared series, okay, is smaller than the original series. So what we need to realize here is that the limit comparison test can only be used, or should only be used, whenever the direct comparison test fails. So primarily, if the direct comparison test fails, try the limit comparison test. And the cool part about the limit comparison test is just this. If you take the original limit, or the original sequence, and divide it by the compared sequence, and that equals a fixed number, then that means that both series converge or both series diverge. So if you compare the two series by taking their ratio and you get an answer, then they both do the same thing. They both do the same thing. So that's why you still want to compare it to something that you know converges or diverges. So let's go ahead and compare this then by just saying, well, I want to compare this, but because the original series is larger than a convergent series, I can't really use the direct comparison test. So instead, look at what I do. I take the limit as n approaches infinity of the original series divided by the compared series. And now I do a little algebra. Well, if I multiply by the reciprocal, I now get 2 to the n over 2 to the n minus 1. But if I plug in infinity, I still get infinity over infinity. So I got to get a little creative here, and let's just divide top and bottom by 2 to the n. So if I divide this by 2 to the n, or if I divide all of these by 2 to the n, then notice that I get this function. And now notice that I took the limit as n approaches infinity. That caused this term to go to 0, so all I was left with was 1. Notice the limit comparison test says if that ratio is a fixed number, then I know that they both converge or they both diverge. Ah, but wait. This is a geometric series that converges. So since the thing I was comparing it to is convergent, the limit comparison test says that this must also be convergent. The comparison tests are actually really powerful tests, okay? So, so that's it. So we've got a few more tests to practice this evening. Make sure that you're practicing. I know that at first, these series are challenging. I agree with you, because it's not always obvious what to compare it to. It's not always obvious what tests to use. The more you practice, the better you start to recognize how to choose an appropriate test.